Welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to do yet another basic use of oscilloscopes video, and we're going to look at taking measurements, and particularly this time we're going to look at measuring rise time, which is perhaps a little bit more involved on an analog scope. So let's start by defining our terms. Measuring rise time then is simply a case of taking a measurement on the leading edge of a wave, as shown there by that red arrow. However, it isn't about measuring the time between peak to peak. Ordinarily, rise time is measured between the 10% and the 90% portion, and quite why that is well beyond the scope of this video, and it isn't always the case, but certainly on most oscilloscopes that have got the ability to measure rise time, it is done using that method. So we then look at the point in time between the 10% and the 90%, and if I extend a couple of white lines up there as cursors, then the distance between those two cursors is the rise time there on the x-axis. Okay, so I've got three circuits here which are going to be producing a waveform for us to look at rise time. First one here is the classic 2-transistor Astable multivibrator. Here's the general arrangement of the circuit, and I'll make sure I put links at the top of the screen to videos that contain more details about these circuits. So that's the first one, and in all cases the blue wire here signifies the output, and this yellow wire will be what I'm going to attach to take a signal out to look on the oscilloscope. The second circuit here is the 555 timer IC. It's the absolute classic arrangement of it. It's running in Astable mode again, with the output on that blue jumper wire there. And finally, here across here is a Schmidt trigger. This is actually a CMOS hex inverter that's got 6 gates on it. I'm just using one of them, and I have tied some inputs low to try and keep the noise down. And this is the simplest of all the circuits, just a resistor and a capacitor, and to be very well behaved, I've put a small capacitor across the supply, as you're supposed to try and keep the noise level down a bit. So those are the three circuits I'm going to use. So now let's look at the oscilloscope screen and see what we can see. Okay, then here's the first of the oscillators. This is the 2-transistor Astable multivibrator, and you can see the display being produced here on the analog scope. So a couple of things to note. First of all, what we're actually seeing is the charging curve of the capacitor there on that rising edge. And if you look closely, I appreciate that's not terribly easy to do, but if you look closely there, in fact, if I just change the time base, we might actually be able to achieve that. Yeah, there we go. I'll just make that a little bit higher there. Yeah, okay. Yeah, so there's the rising edge, which you can see fairly clearly, and you can't see any kind of falling edge there, and that's because the falling edge is so fast that the oscilloscope doesn't have time to display it. In other words, the bandwidth of the scope isn't sufficient to slow the falling edge, so we couldn't, for instance, make a meaningful falling edge measurement of that, because there simply isn't the scope simply isn't fast enough to show it, even on the fastest time base. So what I've done, I've arranged the output voltage of the oscillator to cover exactly 5 divisions, and that will make some sense in a moment, because what I'm going to do in a moment is we'll just take a screen grab of that and we'll actually look at exactly what's going on, but we'll do that on PowerPoint. So here's a screen grab from the digital scope, and as you can see, it's producing exactly the same kind of waveform, but we can now see a falling edge. Now, a digital scope does things a little bit differently. I mean, I think the first thing to say is that the analog scope here has a bandwidth, a maximum bandwidth of 10 megahertz, whereas the digital scope is stated as 100, but in reality it's actually over 100 megahertz. So I would expect the digital scope to be able to display the falling edge. But here's the what I'm going to call normal setting that you would use, where the display on the scope is shown as vectors. In other words, the scope interpolates between its data points and draws a line. Now here is the same thing with dots, and you can see the dots, but the scope hasn't actually managed to draw a complete line there. So what you're actually seeing there is the actual data points. Okay, let's now have a look at exactly how we measure rise time, and we'll do that by taking a screen grab and showing how it all works. Here's a photograph I've taken then of the screen that we were seeing just now, and I've arranged it such that the waveform occupies exactly 5 divisions, just to make my life a little bit easier. Now the time base for this particular photograph, we were at 0.5 milliseconds per division, so in between the two graticules is 0.5 milliseconds. And for completeness sake, we were on 0.1 volts per division, so it's 0.1 volts there. That doesn't impact terribly on rise time because of the way I'm doing this, but for completeness sake I thought we'd show it. So 10% then is going to be 2.5 of the small divisions up from the bottom, and 90% is going to be 2.5 divisions down from the top. I did this just to make it nice and easy to actually show you. And then if we take 2 cursors, one at the 10% and one at the 90% in the time domain, the distance between those 2 cursors, as I mentioned earlier, is the rise time. Now by the miracle of computing, I can actually this animation was produced in PowerPoint, so I'm now going to copy and paste that rise time arrow. So there's an arrow which is exactly the same length, just pasted off on the screen there. And if I now add a 5 division per centimeter graticule there, we can see that that line is roughly, maybe ever so slightly less than 1.6 divisions. But for argument's sake, let's call it 1.6 divisions. So it's 1.6 times the time base, which was 0.5 milliseconds, so that's 0.5 times 10 to the minus 3, which gives us an answer of 800 times 10 to the minus 6. If you follow along here on your calculator, you might get 8 times 10 to the minus 4, but to make it make more sense, I've just moved the decimal point 2 to the right and made it to the minus 6, because 10 to the minus 6 is microseconds, and that means the rise time, according to my analog scope, is around 800 microseconds. And I'm sure this is a very imprecise science here, but that's something like. So let's now have a look what my digital scope makes of that. So there's the 800 microsecond picture we've just seen, and here is what the digital scope makes of it. This is just grabbed, and if you look down at the bottom there, the mean rise time according to the scope is 794 microseconds. Now I promise you that I did a screen grab and I didn't look at it until I'd actually done this maths, so I'm actually rather pleased that would you believe, only about 6 microseconds out. So that's how you would measure rise time on an analog scope that doesn't have nice features like cursors, but of course this day and age we have digital scopes, and most of them will be able to give you the rise time measurement directly if you ask them to. Right, let's now go back to the scope and look at some other waveforms. Okay, so that's rise time, and it's quite encouraging that we can do a fairly crude method of measurement and still produce a meaningful answer there within a few hundred, well, actually within a few tens of microseconds. So was quite encouraged by that. Right, let's have a look at the output of the 555 oscillator. So I'll move the probe over now, and as you can see we've got a much squarer wave, and if I increase the volts per division it's not actually possible to see the rising edge, so it's going to be well beyond the bandwidth of the scope, unfortunately. Even if I increase the time base, we still don't get a line. So the rise time of that is much quicker, and actually the same thing applies. If I just go back to the same thing applies to the Schmidt trigger. If I connect the Schmidt trigger up, again, the Schmidt trigger is likely to produce an even faster rise time, and it's clearly not visible on the scope. So let's now transfer to the digital scope and see what we can see. Okay, so here's the digital scope attached to the transistor multivibrator, and as per the screen grabs that you've seen earlier, we've got a rise time here, mean rise time according to this at the moment of about 782 microseconds. So now I'm going to move on to the 555, and we get something that looks a great deal squarer, and I'm just going to reset the stats so we get a slightly more sensible measurement. And so we're getting now a rise time here of a mean rise time of about 250 nanoseconds. So we're 3 orders of magnitude faster here, so you can see why the scope was the analog scope was struggling to display something as fast as that. And if I just pop onto display, we're currently on vectors. Let's change to dots, and yeah, you can still actually see it is managing to plot some points. And if I now speed up the time base somewhat, the advantage of a much faster scope is that we can actually see that it isn't by any stretch of the imagination actually a square wave, and we're still getting about 242 nanoseconds at the moment, but as you can see on a much faster time base, you're getting a much less obvious square wave, and that's well beyond the capabilities of the analog scope, well, my analog scope. Okay, let's with that same setting on, let's now move on to the Schmidt trigger, see if we can get something sensible there. So I've changed nothing. Let's hop back. That's 555, and that's Schmidt trigger. And as you can see, the Schmidt trigger, boy, is that a much faster rise time, quite considerably. Let's just pop back onto measure, and let's just reset the count. And so according to my scope now, the mean rise time here is 34 nanoseconds. Remember, it was about 250 for the 555, but this is 34. So yes, that's considerably faster. And again, if I speed up the time base, it is also a much smoother looking trace. That's about the nicest one you're likely to see. But yeah, still making it about 34 nanoseconds. So obviously on a scope that can do measurements, that's very easy to do. If you hadn't got a scope that did measurements, you could still nonetheless, you could for instance use cursors, and you could work out the peak to peak. You could take your 10% and your 90% positions, and then you could use your X cursors, and the delta they would give would actually be giving you the rise time. But of course, on modern digital scopes, if you pop onto the measure menu, it will of course measure all sorts of things, including fall time. So let's just add fall time, and let's reset the counters. So we're still getting 34 nanoseconds fall time, but the reason we're getting rise time but we're still getting no fall time, because actually we're not showing a falling edge, are we? So let's slow down the time base to the point where we can actually see a falling edge, and it's very similar. It's about 44 nanoseconds, so it's actually very similar. Apologies for the jumping about, that's probably a dodgy connection on the breadboard. So there you go, yeah, falling edge is very, very fast as well. Okay, there we go. That's the beauty of a digital scope, and plenty of them do have measurement, but hopefully you've seen that even a humble 40-year-old analog scope is nonetheless capable of producing a very credible measurement. And this scope is currently still in calibration. It's less than a year old, and I've got a calibration certificate. So I was quite pleased to discover that when this told me it was 790 something milliseconds rise time for the first oscillator, and the old analog scope was telling me about 800 for maths. I don't think that's doing too badly for an instrument that's at least 40 years old, maybe slightly more. Okay, well there you have it, rise time as seen on analog and digital scopes, and hopefully you've got an idea of how to make measurements in the off chance that your digital scope doesn't offer the facility to actually show you the rise time. But boy, do these digital scopes make life a lot easier for us in the world of electronics, whether it be hobby or professional. So one thing I've not mentioned, and perhaps I should do, is that rise time we were looking at there obviously applies to those oscillators, but it also applies to the oscilloscope. And if you think about what we were seeing on the Hameg scope, where we couldn't see the fall time because the scope simply wasn't quick enough, well, that's got something to do with the scope's rise time. Now, we usually talk about bandwidth when we talk about oscilloscopes, but it is possible to measure rise time to measure bandwidth on a scope using a very fast oscillator, and I've done a video on that, as has Alan Walk. It's definitely worth a look. I'll put a link up there to both of those videos if I can find them, and hopefully you'll get an inkling about how that works too. Thanks very much for watching. If you've liked it, please click the thumbs up, and if you've not subscribed, please subscribe. Both of those things will help the channel, and I would really appreciate that, and we'll look forward to seeing you on the next video.